Example of a coordination complex. You have manganese and you have six water ligands and some chlorides hanging around. So why don't you tell me what the oxidation number is for this now? Not the D count, but the oxidation number. Okay, so let's just take 10 more seconds. Okay, so let's just look at that one for a minute. People did very well on that. So what's the overall charge in this coordination complex? So we can write this out here. There are 6 ligands, and we say that here it's +3 overall because we have 3 chloride ions hanging around with a negative charge. So this tells us that the overall charge on the coordination complex had to be +3. And this, again, is 0, so that means that is +3. So people did very well on that. All right, so then what is the D count? What is it? 4. Right, so we have 7 minus 3 is 4. So we have a D4 system. All right, so now, if you look up there, we have to make a decision about that 4th electron. 3 electrons were easy. 4 makes it complicated. Do we put the 4th one down in the lower set, or do we go up? And so there are two possibilities here. So I have 2 diagrams drawn over here. And you might be in a case where you have a small crystal field splitting energy, or you might be in a case where you have a large crystal field splitting energy. And so there are two different ways the electrons can go. So over here, where you have a small crystal field splitting energy, that's called a weak field. And when you have a big splitting energy, that's a strong field. So with a weak field, there's not that much of an energy difference between them. And so when you're putting in, you do your first 3 electrons. That's always going to be the same. But then the 4th electron, in this case, if there's not a big difference in the energy, if it's pretty small, if it's a weak field, you can put that 4th one up there. Because it takes energy to pair the electrons up. And so you're asking the question, does it take more energy to pair them, or does it take more energy to put one in the upper set? And for a weak field, you say that the crystal field splitting energy is smaller than the pairing energy, or PE. So PE is the pairing energy. And so it takes more energy to pair than it does to bump one electron up to the higher level. So that's what a weak field situation would look like. Now, in a strong field situation, boy, there's a big splitting difference, a big energy difference here. So in this case, the crystal field splitting is much larger than PE, that pairing energy for the electron. So it's better to pair than to put one up. I can't even reach those. That's really far up. So I'm not going to do that. I'm just going to put them in here. I'll put the first 3 in. And then the 4th one is going to go down where I can reach it. I don't have the energy to put it up there. So that's a strong field. Weak field I can handle. Strong field, I'm going to try to pair them all. I'm going to try to pair them all up. So now we can write the different DN electron configurations for these 2. So let me just stick that there. So in this case, if we have our DN electron configuration. So we have 3. In the T2G, we have 3. And in the EG set, we have 1. So that is our electron configuration for this weak field case. And for the strong field case, we didn't put any up in the EG, so we just have T2G 4 electrons in that set